Hello, and welcome to Lab 4, which covers circuits. My name is Eric Turner. So some of the goals for this lab. To successfully predict the behavior and interactions of resistors in both parallel and series circuits. To use multimeters to measure current and voltage differences. That's going to include ammeters and voltmeters. And to observe ohmic resistors and capacitors. Some background. A series circuit is one with a single path for current to follow, and parallel denotes one circuit that has two or more paths. An ammeter measures the current of the circuit at the place you position it. A voltmeter measures the voltage difference around some resistor, capacitor, or some other output. Some of my hypotheses and results that I found. So the first question asks us to predict the current in a circuit pictured to your right, and using the voltage that we were given for the batteries and the resistance in each resistor, I predicted that the current would be 0.02 amps. And after putting the circuit into CCK, I found that it was in fact 0.02 amps. Moving on, it asked us to switch the direction of one of the ammeters and to see what would happen. And after flipping it, you can see in the top right image that it made no change. The output is still 0.02 amps. After replacing the ammeter with the probes of a voltmeter, the ammeter said 0 amps and the voltmeter read -3 volts. Why is that? This is because a voltmeter is very high in resistance. That's why typically connect them in parallel so that you don't affect the circuit. But in this case, we're putting it in series. So it's acting as a very strong resistor, and that's why you see no current readout in the ammeter. In this exercise or this question, we were asked to determine the voltage drops around the whole circuit, and in the table you'll see my results. From C to D and from E to F, which is across both resistors, I found a drop of 0.959 volts and a drop of 2.041 volts. You start at +3 and then you end at 0 because between the two resistors you drop 3 volts. And the current in this scenario was still 0.02 amps. For this part, my prediction was that all voltage drops should sum to the magnitude of the total EMF, just as we saw in the table previously. And I found that that was true. My voltage drop for the whole circuit was -3, which is equal in magnitude to the EMF of 3. So I was correct. This is just a visual for the voltage drops across the circuit. From A to B, that's where the batteries are. So you see it goes from 0 to 3. And then from C to D, that's the 47 ohm resistor. It drops about 1. And then from E to F, you'll see that it drops again across the 100 ohm resistor, about 2. Why does a voltmeter fail to alter the current when we're placing it around the circuit? As I said previously, usually when you use a voltmeter, you connect it in parallel. And when it's in parallel, it blocks the current from going in that path because it has such a high resistance. So it alters the circuit almost none. And why does the current increase when the ammeter is put in parallel? It's because you're altering the equivalent resistance of the circuit. By putting that in parallel, you're changing how that resistor is coming into touch with the other resistor, which in turn affects the total resistance of the circuit. Here we were asked to determine the resistance of the two resistors, the wire and the ammeter. So I created this VIR table, which is helpful when determining or for when analyzing circuits. And the first thing we know is that because it's in series, the current is the same everywhere. So we know that it's 0.06. The first thing we can do is we can look at the total voltage, which is 3, and we know the total current, so we can then calculate the total resistance of the circuit, which is 50 ohms. And then from there, we can head up to either resistor and determine the resistance for each of those. And then we know that 15.98 and 34.01 is equivalent to 50, so we know that the wire and ammeter both have to have resistance 0, which in turn means that the voltage across them is also 0. Moving on to the RC circuits. So my observations were that the light bulb grows dimmer the longer the capacitor charges and the longer it discharges. And from that, we can confirm that current is decreasing with time. So the graph of ln dV over dV naught versus time. This was the best way to analyze the situation because it gives us a linear plot in which we can use the slope to find the RC value of the circuit. In the table to the left, you'll see that in the numerator of all those expressions, that's the incremental voltage that I found when measuring. And the denominator is 9, which was the initial voltage of the capacitor when it was fully charged. The graph, as you can see, has a linear fit to it, but the most important takeaway here is the slope, because that's what we're going to use to find RC. So when analyzing it, we know that the slope is negative 1 over RC, or the negative reciprocal, and we know that the slope was negative 0.167391. So using the equation at the right, we can find RC to be 5.9704 seconds. The RC of the CC circuit was 5.3251 seconds, so I'd say that that's close enough to be considered accurate. So some important questions to ask ourselves. Would there be a difference if we used a real ammeter on a real circuit? And the answer is yes. In this case, we're looking at an ideal ammeter in which the resistance is completely zero. But in real life, almost nothing has zero resistance. So we would find a slight voltage drop across a real ammeter. And second, is there a discrepancy between the time to completely charge a real capacitor and a virtual one? Yes, much like the first question here, we're looking at an ideal scenario where the resistance on the wire is zero as well. In the real world, the resistance in the wire is not going to always be zero. It's going to have some small value to it. Even that alone will change the time it'll take to charge a capacitor or discharge. So in the real world, you'd see that there'd be a slight longer time to charge or discharge. Thank you.